In this lecture, I'm going to introduce the fundamentals of operating systems, what they are, what they do, and why they're important. Now, what's an operating system? Well, it's a layer of software that provides two important services to a computer system. It provides abstraction and arbitration. Abstraction means hiding the details of different hardware configurations so that each application doesn't have to be tailored for each possible device that might be present on a system. Arbitration means that the operating system manages access to shared hardware resources so that multiple applications can run on the same hardware at the same time without interfering with one another. Now, these hardware resources that need to be managed include the CPU, the hierarchy of memory, all the input-output devices on the system, and to some degree the power and system management features of the system. Many of these features are handled directly by the hardware, but the operating system is involved, particularly in energy conservation. Now, the abstraction features of the operating system allow hardware devices manufactured by different manufacturers to have the same interface within software for applications to use. These hardware devices all have different low-level instruction sets. They all have particular capabilities, features, and details that are unique to each hardware device. If we didn't have a common interface into these hardware devices, first of all, our variety of hardware might be limited, but worse, every application on the system would have to be programmed to use every single device on the system. An example, back in the 1990s, computer games often required internal programming for specific video cards and specific sound cards. It was often necessary to go into the settings for each game and tell the game what type of video card you had, what type of sound card you had, for the purpose of configuring the game to use that particular hardware. Imagine if that had to be done for every single application on the system, including, say, a calculator or a web browser. That would be a very untenable situation in terms of being able to make use of computers the way we use them today. Also, what if we could only run one program at a time on a computer system? Years and years ago, that was the case. However, a modern system is running multiple applications simultaneously, and it's up to the operating system to ensure that all these applications can access resources. So each CPU is divided among the different programs. Each program gets access to memory, input-output, as well as disk. And in an ideal world, the operating system also enforces policies that isolate applications from each other, so that a crash in one application doesn't take down the entire system or other applications. Now, of these examples, do we have a situation where we have abstraction or arbitration? Well, first example supporting both Intel and AMD processors. This is an example of abstraction. We don't have to write separate software for an Intel processor relative to an AMD processor, at least for 99.99% of applications. Simply write the application once, it will run on either processor. Switching between applications is an example of arbitrating hardware resources among the different applications on the system. Separating memory allocated to different applications is also an arbitration activity. It keeps one application from overwriting the contents of memory that are being used by another application. Enabling video conferencing software to use different camera devices. This would be an example of abstraction. The video conferencing program just has to know how to use a camera interface that the operating system provides, and then different cameras from different manufacturers can be used without having to write the application, the video conferencing program, to be able to talk to each individual camera. Similarly, accessing two different hard disks from two different manufacturers. Any underlying detail differences between those drives can be handled by using the operating system to abstract away the details. Sending and receiving messages over a network is both abstraction and arbitration. On the one hand, we're abstracting away the details of each particular network card to be able to send and receive the message. On the other hand, we're sharing that network card among all the different applications on the system. Now, we can think of the system in terms of layers. At the bottom of the layer cake, we have the hardware. This is what executes the software, the top three layers. The operating system is the middleman, so to speak, between the applications and the libraries and utilities upon which the applications depend and the underlying hardware. Specifically, the core of the operating system, or the kernel, so named after, say, a kernel of corn, is the minimum piece of software that's needed to share the hardware between the different applications. Whatever lives outside the kernel that is software is said to be in user space. That means it's application code, or sometimes even parts of the operating system, that are not strictly necessary to share the hardware or abstract away its details. Now, operating systems implement a common mechanism for allowing applications to access the hardware, which is abstraction. And the applications make requests from the operating system to go and access the hardware or other features by making system calls down into the operating system. This is called entering the operating system, or entering the kernel from the top half. Operating systems are also able to alert applications that hardware has changed. Perhaps a network packet has come in. Perhaps the user has pressed a key on the keyboard. These alerts are delivered via a system called interrupts and refer to entering the kernel from the bottom half, from the hardware side of the operating system. We should also note that operating systems can manage and terminate applications by sending signals to those applications. Now, there are a wide variety of operating systems out there. They basically fall into two categories: Microsoft Windows, which is not Unix, and everything else, which is Unix. Microsoft Windows systems, non-Unix systems, are the most popular desktop operating systems at the moment. However, they're rapidly being eclipsed by tablet devices, most of which are running Unix-style systems. Windows is typically pre-installed by PC manufacturers, which accounts for a good portion of its present popularity. Unix systems, on the other hand, are installed by the end user, except for commercial Unix systems and Mac OS X. Mac OS X is probably the best-selling Unix system of date. And Linux, which includes the Android platform, is probably second. Now, there are some mainframe systems out there also, some of which are Unix-like. Some use custom operating systems. There are a variety of players in the embedded systems market. However, that's presently dominated by Android, with Apple's iOS, which is based on Mac OS X, in close second. Others, Symbian, BlackBerry OS, TinyOS, are confined to smaller markets. Now, the idea behind the Unix systems began with a time-sharing system started in 1964 called Multics. And the idea behind Multics was to make computing into a remote service that could be accessed by terminals using telephone lines. It wasn't terribly successful because dial-up connections of the time at about 9600 baud were rather slow. However, Canada actually did have a Multics system deployed and used it as part of their national defense network until the year 2000. Multics is remembered, however, primarily for its influence as a multi-user shared system. And today, with cloud computing, there's some significant parallels between some of the cloud computing models that we use and some of the ideas that were pioneered back in the Multics system. Now, Unix was actually a play on the term Multics. It was developed by Bell Labs in 1969. It's actually a trademark term, so some authors use Starnix to refer to the family of systems and use the word Unix only for the commercial distributions. The original Unix systems were commercial distributions, with free variants of BSD and Linux coming along late 80s and early 90s. Now, Unix systems are time-sharing systems in that they support multiple users at the same time, but they're designed to be run on local computer resources instead of remote resources. The Berkeley system distribution, which was based on AT&T's commercial distribution, was one of the first open source Unix systems to emerge. It was based on the commercial distribution, so AT&T sued UC Berkeley, but an eventual settlement allowed Berkeley to distribute BSD freely in both source and binary form. Today's descendants of BSD include FreeBSD, OpenBSD, and Mac OS X, which is based on the Unix BSD system. Linux, however, was an alternate approach to getting a Unix-like kernel running on a computer system. This was started by Linus Torvalds as an undergrad at the University of Helsinki, released in source code form in 1991, and often combined with a set of user space utilities and libraries created by the GNU project. Thus, the resulting combination is sometimes called GNU/Linux. It has been commercially successful for many device classes, including web servers, network and embedded devices, and mobile phones. Some people, including myself, use Linux as a desktop platform, and it does have the benefit of having the one kernel that's scalable from embedded devices all the way up to supercomputers.